So now we want to ask, so now we've confirmed, we understand the wave, we reviewed our topics here, now we know what's going on. So now we want to figure out how fast does it go, right? The wave goes really fast. How fast is it? Just want to turn that off. There we go. Yeah, so let's look at the wave speed now in more detail. All right. God dang it. No, Lord. Oh, that's stuck up there. Yes. How fast? Is this starting to look like being at the zoo? I don't know. Is the wave. The wave. How fast is the wave? Okay, so you just saw one flying by. You can see it moving here. So the quick way to get the speed in terms of what you know would be to say, well, I would say I'd do it like this. The speed is that it goes a full wavelength over a full period, right? That's how fast it's going, right? The whole sinusoidal pattern moves from here to here. And by definition, that takes a period. So if you know that wavelength and you know how long that takes, that's the speed. So the simplest formula for speed is that it's lambda, the wavelength, over t, the period. If you're really into frequency and not period, you can say that lambda is the frequency. I'm sorry, that the speed is frequency times lambda. Right? That's it. That's all there is to it. V equals frequency times wavelength. But you know that in sort of grown-up physics, we like to use radians. We like to use radians. So what we do is we take our V, we take our lambda over, let's take our lambda over period, and we multiply it by 2 pi over 2 pi. Can you do that? Yeah, right, because 2 pi over 2 pi is 1. So just multiply it by 1. We can also multiply it by 1, again. Okay, wow, look at that. And then you can look at it and start regrouping it and saying, oh, this lambda over 2 pi, we called that k. And then what is 2 pi over t? That's 2 pi radians over the period, that's omega. Right? So you can also say V, no, I'm sorry, wait. What have I done here? This is 1, I'm sorry, lambda, yeah, okay, start over. K is 2 pi over lambda, this is 1 over k. Of course, yeah, k is in the bottom, right? And then 2 pi over t is, of course, omega, yeah. Right? So the way physicists think of it is in terms of omega and k. V is omega over k. But this still isn't even how physicists think of it, right? We rearrange it to make the most famous statement of the problem, which I'm going to look up because I've now screwed this up and thrown myself off. Omega is vk. Right? So if you're solving problems and you don't really want to think in terms of radians, I would remember that v, the velocity, is the frequency times the wavelength. But if you go further in physics, you'll see this written down all the time. Omega is vk. It's the exact same thing. It's just one is in radians and one isn't. The way I really remember it is, how many people here are from Dallas? Yay, DFW, right? So when I was a kid, we called this W for the wavelength. And we said, oh, V equals FW. And I thought, oh, DFW. Right? So that's how I actually remember it. So that's why every time I teach and talk about physics ever, in my head I have to convert from DFW to omega equals VK. So that's why I screwed it up. I was thinking about Dallas. And I was from the wrong side of the tracks in Dallas, so, it takes me time to recover. Okay? Now this is sort of how the wave speed relates to the frequencies, the time frequency and the spatial frequency. But each wave medium, the wave speed itself depends on properties of the medium. Of the medium. Right? So if I gave you like a wave equation, and from it you could come up with omega and k, you could say, okay, I know the speed of the equation. And then you might mistakenly say, oh, it's determined by omega and k. But not really. That's just more how it relates to omega and k. It's really physically determined by how stringy, heavy, and pulley, and stretchy the medium is. All right, so for the string, it looks like this. The velocity is the square root of the tension over the mass density. I think we wrote that last time. All right, tension over mass density. So if you put everything in whatever, newtons per meter, coulomb squared, blah, 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 it'll come out in meters per second. If you put tensions in newtons and mass in kilograms per meter, it'll come out. Why do we have to wait until the middle of November for it to be warm in here? I don't know. I don't know. Let's see. I could prove this to you if we want. We could actually know the properties of that string. If we want, we could have a quick look and calculate it real fast. Let's see if we can do it right. We're going to do a demo through the magic of videotape here. So the typical string that I set up that you see, that stretchy string, has a mass density of 0.0039 kilograms per meter. So we're just going to take this little corner of the board and do the demo now. Mu equals 0.0039 kilograms per meter. This is for the string. Okay. Yeah, okay. And the tension we can actually set. So if I look at this thing, and the tension was set at 1.27 newtons. So for yourself, on your phone or whatever, be calculating what you think the velocity is going to be. That'll be fun times, right? The velocity, let's see, so the tension's 1.27 newtons. All right. So from that, we should be able to get the velocity. It's the square root of t over mu. So it equals blah, 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 number. It equals 18 meters per second. That's pretty fast, right? World-class 100-meter sprinter is going 10 meters per second. So that's twice as fast, almost. Okay? So now we're going to watch it at a few speeds, and we're going to see if we get the right answer, right? So here we go. So here's a pulse going by, very fast. It's in slow motion. 1/10th speed. Look at it go, very fast. Oh, I have the lights on. 1/50th speed. Look how fast it's going by. So it went through those marks in 3.33 seconds at 1/50th speed. It got from there to there. So let's see what we get. If we did this as a demo, we'd say, how fast did it go? Here to here is 1.2 meters. These are 30 centimeter marks, 34. So V is 1.2 meters in 3.33 seconds over 50, because it's 1/50th of a second, or it's slowed down by 50. What do you get? 1.2 divided by 3.33. That's a factor of 4 or 3 times 50. It's 1. You get 18. You get 18 meters per second. Okay. So if you measure all this and you run it, it's exactly right. Okay. So now you can look at it and say, so does this mean that this is the equation for the speed for every wave? It seems like if it worked so well for this wave, it should be the universal speed. And the answer is no, because remember, the wave speed depends on the properties of the medium. So if you calculated the wave speed for sound, you're doing it with like the ideal gas law, not tensions in a string, and you'd get something else. But it would still be, it's usually kind of like the square root of something that has to do with how stiff it is and something that has to do with how heavy it is. It's always kind of similar. But that equation is only for the string. This equation is for any wave. Okay? This is general mathematics of waves. This is physical. Okay?